Hello, I'm Ed Ackerman, and as CTO of PSI, I've been heavily involved in PSI's STAR development since the beginning. This is a demonstration of hardware developed by PSI, that's Photonic Systems Inc., that lets us receive an OFDM signal of interest while simultaneously transmitting another OFDM signal occupying the same frequency band. The Simultaneous Transmit and Receive, or STAR capability, is enabled by PSI's STAR chip. We have integrated the STAR chip with other hardware necessary for this demo inside this component we call a STAR box. Our signal of interest is an OFDM signal of the type used in LTE communications. We generate this OFDM signal using a software-defined radio whose output we broadcast from this antenna, and which we control using this NUC computer. The OFDM signal consists of 180 separate carriers with 15 kilohertz spacing, occupying a 3 megahertz bandwidth. All 180 of these carriers are modulated sequentially by QPSK signals of about 67 microsecond duration with a 4.7 microsecond cyclic prefix. Therefore, this demo mirrors what is done in LTE, except that for our data, we're going to be just generating ones and zeros randomly. We've connected the receive port of our STAR box to a spectrum analyzer and are also displaying on this laptop how the receiver is demodulating the digital data in real time. To begin the demo, we will start with simply receiving the OFDM signal of interest. Since there is no transmit signal to suppress yet, that function of the STAR box is currently off. So with this antenna over here broadcasting the 180 OFDM carriers, here's what the received signal looks like at RF on the spectrum analyzer. We're centered here at 88.1 megahertz, and the bandwidth we're seeing is 3 megahertz. The demodulated received signal, consisting of a random stream of ones and zeros, is shown on this computer display, which shows the demodulated signal as a function of time. We can also transmit all zeros, and when we do that, we see that the demodulated receive signal is all zeros, with the exception of an occasional 1, which represents a bit error. Now we're going to go back to transmitting a random stream of ones and zeros. Now, while that OFDM signal of interest is being received, we're going to show what would happen if we suddenly tried starting to transmit here from this antenna a different random bunch of ones and zeros on 180 OFDM carriers in the same 3 megahertz bandwidth at 88.1 megahertz as the OFDM signal that we're currently receiving, but without the benefit of PSI's STAR chip technology. Currently, with no transmit signal on, we have the STAR box in a mode where it is not actively working to isolate its receive port from any reflected transmit signal. So now when we do turn on a strong OFDM transmit signal, like so, we'll see on the receiver's output that it is frozen because two OFDM signals are strongly present and it cannot resolve them from one another in order to demodulate them. Now we'll activate the STAR chip's transmit suppression mode, and you'll see that we are back to recovering the OFDM signal of interest. In other words, this antenna is transmitting our strong OFDM signal, but simultaneously our receiver is able to recover the receive signal we want, which is the OFDM signal being broadcast from the other antenna. Let's now change that data being broadcast to all zeros, and we'll see the effect of doing that here on the receiver's demodulation plot. So we went through that demonstration fairly quickly without explaining much about the STAR box itself. Now let's go back and talk a little bit more about the STAR box, and then we'll demonstrate its performance a second time, stepping through the demo a little more slowly. The STAR box is essentially a 3-port component that connects an antenna at this one port to both the transmit and receive ports of a transceiver simultaneously. This is the transceiver sitting under our STAR box. The STAR box does that in such a way that it isolates the receive port of the transceiver from the powerful signals supplied by the transmit port of the transceiver. This isolation cannot be simply provided by any passive 3-port component because some of the strong transmit signal will always inevitably reflect off of the antenna and back to the receiver unless a specially designed component like our star chip inside our star box performs active cancellation of such reflections. And achieving this isolation is very important because the transmit signal is very strong, and so without thorough isolation, the receiver would not be able to recover the much weaker signal of interest. So now let's demonstrate the star box performance a second time. Let's begin without the received signal of interest present, because doing so will let us see more quantifiably how well the star box is isolating its receive port from strong transmit signals. Without the received signal of interest being broadcast from over there, we'll start by showing how much of the strong transmit signal is being reflected by the antenna back into the receive port of our transceiver, with, again, the star chip deactivated. Across the 3 megahertz bandwidth of the transmitted OFDM signal, we're seeing about minus 50 dBm at the receiver. Earlier, we had measured on this spectrum analyzer the transmit signal present at the antenna port, and its level was about minus 40 dBm. So the inherent transmit-receive isolation of our star box, even without the star chip activated, is approximately 10 dB. But now, turning the star chip back on, if you would, lets us do a before and after comparison. There we go. And we see that it knocks the transmit signal down by at least another 30 dB, such that it's below now our background FM signals that this antenna is picking up near 88 megahertz. Therefore, the total transmit-receive isolation of our star box across this 3 megahertz instantaneous bandwidth is at least 40 dB. That is, the 10 dB of inherent isolation plus the 30 dB of active cancellation beyond that we just saw. Now, while the transmit signal is being actively canceled, let's again turn on the remotely broadcast OFDM signal and show its successful reception over that 3 megahertz band. And there it is on the spectrum analyzer. And over there are the demodulated data displayed on the laptop. And just to show, again, that what we're displaying there is what's being broadcast, when we once again change the data on the OFDM signal back to being all zeros, we see that change on our time domain display. And again, you see the occasional error. That concludes PSI's demonstration of our star box's ability to recover OFDM signals using an antenna that is simultaneously transmitting stronger signals in the same frequency band. Thank you for your attention. Please email me any questions you have. My address is eackerman@photonicsinc.com.